Hi guys, thanks for taking notes while we're out today. If you are Mrs. Epley's class and you're noticing that page 38 in the top right-hand corner, and we have not done page 37 yet, please number a page for 37, skip it, and then number a page for 38 and take these notes there. Today we're talking about temperature and pressure units and which ones we use in science. Your essential question is, what units do we use to measure temperature and pressure? Will you please label page 38, temperature and pressure units, and write your essential question. If at any point in this video you need to slow down, please feel free to pause the video, take the notes that you need, and restart. All right, let's get going. So what happens to pressure when we increase the temperature? Well, we did a lab with this in both Chaska and Chan classrooms where we looked at pressure and temperature. With Mrs. Epperly students, we haven't really looked at the graphs yet, but we'll come back to that when I return to school. So temperature and pressure is a direct relationship, which means when one increases, so does the other. When pressure increases, so does temperature, and temperature causes an increase in pressure. What specifically happens, though? If we double the temperature, what happens to the pressure? Well, this graph's not a great place for us to make an estimation because we don't have any numbers, but think about it in your head, come up with something. Pause the video if you need a minute to think, and then let's talk through and see if your prediction is right. If we take a look at this graph, we've got temperature in degrees Celsius on the x-axis and pressure in kilopascals on the y-axis. I'm going to find two data points and see what happens if I double temperature. So at 15 degrees Celsius, I have a pressure of 99. When I double my temperature to 30, my pressure goes up, but not very much. It definitely doesn't double. My prediction was that if I doubled temperature, my pressure would also double. This graph isn't showing that. What about you? Was your prediction right? If I zoom out on that same graph, I see that when my pressure is 0, I have a negative temperature. What temperature is that in degrees Celsius? Well, I'm between negative 250 and negative 300. That number is negative 273. So why negative 273? Well, when we look at negative 273, that's when pressure is equal to 0. The temperature is negative 273 degrees Celsius. When pressure is 0, how are particles moving? Well, when we did the thermometer lab, we talked about pressure, and we said that pressure was because of particles moving and the collisions between particles and the container walls. If pressure is 0, that means there are no collisions. If there's no collisions, how are particles moving? They aren't, which means at negative 273 degrees Celsius, there is no particle movement. We call that absolute zero. In science, there's a second way to measure temperature. That temperature is measured in kelvins. So 0 kelvins is absolute zero. That's negative 273 degrees Celsius. That's when particles stop moving. So for chem, we're going to measure things with a thermometer in degrees Celsius, but when we work with those temperatures, we're going to convert them into Kelvin. I'm going to give you a couple of equations to make that happen. Before moving on to the next slide, make sure you have the important information from this written down. Now let's take a look at a graph measured in kelvins. So temperature in Kelvin measured and pressure in kilopascals on the y-axis. This time, if I think back to my prediction, I thought that if I doubled the temperature, I'd double the pressure. Well, at 100 degrees Kelvin, my pressure is 20 kilopascals. If I double my temperature to 200, my pressure is 40 kilopascals. So I was right. When you double the temperature, you do double the pressure, but only if it's measured in Kelvin, not if it's measured in Celsius. We have a standard temperature, which is 273 Kelvin or 0 degrees Celsius. Kelvin equals Celsius plus 273, and Celsius is Kelvin minus 273. Make sure that those two equations go in your notebook on page 38, as well as the information that 273 Kelvin or 0 degrees Celsius is considered standard temperature. Keep in mind that those two values are the same. 273 Kelvin or 0 degrees Celsius are the exact same feeling temperature, and that's when particles stop moving. At sea level, we've got a lot of particles, and as we go up and up and up, the air gets thinner. If you've ever been up on the top of a mountain and it's harder to breathe with elevation, that's because there are less air particles there. So at sea level, there's a lot of pressure, and as we go up, the pressure decreases. This is a standard pressure, just like a standard temperature. So it's based on the air pressure at sea level, and we can measure it in a bunch of different units. When I say we're measuring it in a bunch of different units, if you think about measuring the length of your desk, you could measure it in inches or centimeters or millimeters or meters. All of them are going to give you a different number, but the length of the desk remains the same. So we can measure the air pressure at sea level in a bunch of different units, but the pressure is the same thing regardless of how we're measuring it. So a couple of units that we use are ATM, which is atmospheres, or kPa, which is kilopascals, mmHg is millimeters of mercury, and PSI is pounds per square inch. That might be the one you're the most familiar with, as that's how we measure the amount of air pressure in our car tires. So standard temperature and standard pressure is abbreviated STP. Kelvin is equal to Celsius plus 273, 273 Kelvin or 0 degrees Celsius. 1 ATM is 101.325 kPa, is 760 millimeters of mercury, is 14.69 psi. In your notebook, I would make sure to have these equivalencies. And when I mean equivalencies, I'm saying that 1 ATM is the same as 101.325 kilopascals, is the same as 760 millimeters of mercury, is the same as 14.69 psi. Think back to the example I gave about the desk. We're measuring the same thing, we're just using different units. Because standard pressure is all related to air pressure at sea level, these are all the same thing, just a different way of saying it. Now we're going to do some pressure conversions and some temperature conversions, and these are really important to put into your notebook so that you have the work, and next time you get stuck, you have something to check. So if you think back to physics when we did dimensional analysis and converted units, this is the same thing, but this time we're talking about pressures. So, as always, we start with what we're given. We have 200 kilopascals. I put that into a bracket. I set up my next bracket, and I put on the bottom the same unit. Remember that we know that 200 kilopascals is the same as 200 kilopascals over 1. That just shows us that kPa is on the top of the first fraction. kPa goes on the bottom of the second fraction. I want to turn it into ATM, so I put ATM up top. Now I can look at my equivalencies and plug in some numbers. The number next to kilopascals is 101.3. I know that you wrote down 101.325, but it's okay to shorten it to 101.3. The number next to ATM is 1. To solve, my kilopascals units cancel out. I'm left with units in ATM, which means my answer will come out in ATM. When I solve, I take 200. I multiply by what's on the top of the next fraction, and I divide by what's on the bottom. So in my calculator, I would plug in 200 times 1 divided by 101.3. I will get an answer of 1.97 ATM. This process is the same for the next two. Feel free to pause the video and try them, and then come back and see the work to see if you're right. I set up my fractions the same, make sure that my units cancel out, and I plug in my equivalencies from the slide before. 2.02 times 760 divided by 1, I get an answer of 1,532.2 millimeters of mercury. Last but not least, I start with what I'm given, I set up my fraction to get my units to cancel, and then I use the numbers from the previous slide for my equivalencies, put them into my fraction, Take 748 times 101.3 divided by 760 to give me 99.7 kPa. We can also convert temperature units. The first one is 37 degrees Celsius. That is the average body temperature. I take 37 plus 273. My answer in Kelvin is 310. Whenever I have something in degrees Celsius, I add 273 to get my answer. If I am starting in Kelvin, like the next one, average room temperature is 298 Kelvin. I subtract 273 to get degrees Celsius, 25. Number 3, I'm adding 273 to turn it into Kelvin, and water boils at 100 degrees Celsius or 373 Kelvin. Last but not least, the coldest it's ever been in Minnesota is 222 Kelvin. I subtract 273, and that is negative 51 degrees Celsius. That was in Tower, Minnesota, a teeny tiny town where it's typically pretty darn cold. Last but not least, just for your interest and understanding equivalencies, here is a thermometer chart of Kelvin versus Celsius versus Fahrenheit so that you can see how the three temperatures compare with each other. That's it for temperature and pressure notes. Make sure you have everything you need to on from the slides into page 38 of your notebook. Thanks for watching.